Dear students, today we will do a theorem known as the circle theorem. In this theorem, we will see that how a circular boundary placed in a flow region changes the complex potential of the flow. Actually, you have learned the image of a source or a sink or a doublet with respect to a circle. In that study, we have seen that if there is a circular boundary placed in a flow region, then we can describe the flow at a point with the help of image system. So that is one way of solving the problems containing this. There is another way using the circle theorem. So first of all, we will see what is the circle theorem. It is also called Milne-Thomson circle theorem. If you study the circle theorem from the books, it is quite a little bit confusing. So I am writing its statement in a very simple way. First of all, I will write the statement and then I will explain the meaning of that statement. So statement is, let Fz be the complex potential for a flow having no rigid boundaries such that there are no singularities of the flow within the circle, which is actually the cross section of a circular cylinder within the circle mod z is equal to a. Then on introducing solid circular cylinder of radius a, that means the cross section is a, of radius a, in the flow, the modified or the new complex potential will be Fz plus f of a square upon z for z greater than or equal to a, that means outside the cylinder, and no new singularities are introduced into the flow outside z is equal to a. Whatever singularities will be introduced will only lie within or on the circle. So this is the circle theorem. I am repeating. Suppose you have a flow region and that flow region has no rigid boundaries, and the complex potential describing the flow region is Fz. Then the theorem says that suppose that if there is a region circular region where there are no singularities. Suppose we introduce a circular boundary in the flow region having no singularities. Simply that in the portion where there are no singularities, we are introducing circular boundary. On introducing it, naturally the flow will be modified and the modified complex potential will be given by Fz plus Fa square upon Z. If you look at this expression Fz plus Fa square upon Z, you will see that this Fa square upon Z is nothing but complex potential of Fz. So this is the complex potential for the modified flow region. And one another condition is, or one another result is, that no new singularities will be introduced in the flow region outside that cylinder. Whatever new singularities will be introduced will lie inside the circle. So this last condition simply says that the flow will not be disturbed. No singularities will be introduced in the flow region. Flow will not be disturbed. So first of all, we will look at its proof and then we will use it in some example. Suppose there be a flow region. Let the flow region with no rigid boundaries is described by W1 is equal to Fz. Subjected to the condition what is the condition? Here we have written it that there are no singularities of the flow within the circle. So this is the condition. Condition that there are no singularities. Whatever singularities are there will be outside. No singularities inside. Z is equal to A. It simply means whatever singularities are there will be outside Z is equal to A. Now we place a circular cylinder of cross section Z is equal to A in the flow region. Now naturally it is a rigid cylinder and there is no flow across it. So this rigid cylinder will work as a streamline. So there will be some stream function along that streamline. Let psi be the stream function along that streamline. And then we know that stream function is constant along the streamline. So that psi will be constant and we assume psi to be 0. So let the stream function psi is equal to 0 along the rigid circle, rigid circular boundary behaving as streamline. Now if I say that on introducing a circular cylinder our psi becomes 0. So it may happen only when your W1 which was Fz and now introducing some cylinder it will be modified and the modified will be W2. This is possible. Psi would be 0 only when W2 is real. It is for original flow. Now for modified flow, W2 for modified flow should be of the form that psi is equal to 0 for it. Now psi is its imaginary part. So we want in W2 there should be only real part. Now how W1 containing or expressed as Fz will contribute in such a way that W2 will become real only. So whatever we are going to add in W2 is W1 as well as the complex potential due to modified flow. So our new W2 will be real only if this is W1 plus for the modified flow or on introducing the circular cylinder, complex potential of Fz should be added to W1 so that W2 will become real. We may write it as Fz plus because z bar is equal to a square. So z bar is a square upon z. So it is f a square upon z. You can see that this is also the inverse point of any point either inside the circle or outside the circle. It will represent the inverse point. So this is the first part of the theorem, that for the modified flow or after introducing a circular boundary, the modified flow may be represented by Fz plus f a square upon z, where z bar is equal to a square or the radius of the circular boundary is a. Now we know that singularity of Fz lie singularities of Fz lie कहाँ लाई कर रही थी ये outside z is equal to a. This implies singularities due to f a square upon z. It is the inverse point. So these will lie inside z is equal to a. यदि इसकी आउटसाइड है तो ये इन्वर्स पॉइंट है तो इसकी इनसाइड हो गई. दिस इम्प्लाइज इंट्रोडक्शन ऑफ a circular boundary does not introduce any new singularity in the flow region outside z equal to a. That means your flow will not be disturbed. So it is all about circle theorem. Now with the help of an example, I'll show that how we use the image theory and how we use the circle theorem. So come to an example. Suppose I take example from the book. This example has a extension part. In first part we will use the image system, and in they want to find some theoretical result. For example, if you look at this example, the velocity potential when there is a source and an equal sink within a circular cavity show that one of the streamlines is an arc of the circle which passes through the source and the sink and cuts orthogonally the boundary of the cavity. You look at this example. This example has two parts. In first part, find the velocity potential. That means you have to find phi. When there is a source and an equal sink within a circular cavity. So this is the first part. So we will concentrate on the first part. This is a circle, or you may say this is the circular cavity. And in this circular cavity, you have a source and a sink. Suppose it is a point where you have a source and it is a point where we have a, this is the point P having a source, and let it be the Q having sink. Now the question says, find the velocity potential when there is a source and an equal sink within a circular cavity. So our image system says that I should take this P at the center, in the line of the center. Suppose this is the center. Take P here and then Q here. Let it be P and it be Q. Naturally, from the image system, this source at P will have a source of equal strength at P dash at its inverse point, such that what is O relation between OP and OP dash? It is A square, because there is a source. So this source is at P. Take this source at P. Now, and an equal sink. Yes. This source will have another source of the same strength at P dash and a sink at O by the theory of image system. And an equal sink, so this is at Q. Because there is a sink at Q by the image theory, it will have, I'll draw a type of circle क्योंकि मुझे ये इसके थ्रू ही लेना है. तो you draw a line. This will be the inverse point of Q dash. Here again there will be a sink and a source at O. This is all due to image system. Now what you do, you draw a circle with the help of these 2 points. And joining these points also. इस तरह से हम एक सर्किल बना लेंगे. जो इधर पी क्यू से होता हुआ जाएगा और इधर P डैश Q डैश से होता हुआ जाएगा। तो ये जो P डैश डैश Q और P हैं, ये कैसे पॉइंट्स हो गए? These are cone cyclic points because these are lying on the same circle. This property, the property of cone cyclic angles will be used. Cone cyclic points will be used in this question. Now we again come to the first part. You have to find the velocity potential when there is a source and an equal sink within a circular cavity. Now by the image system, first of all you have a source M strength at P. Its image system implies a source of strength M at P dash plus a sink of strength M at O. P means, suppose P point is taken as C, so it is at C0. And the point P dash will be, naturally point P dash will be A square upon C, because the multiplication here, your OP, here OP is C, so OP dash is A square upon C. And you have a sink at this, so sink at the point 0, 0. Let us take this angle to be alpha. Now second, a sink of strength M at Q. So what is the location of Q? At Z is equal to B e raised to the power I alpha, because it is making an angle alpha with x-axis. So OQ will have some distance and it is inclined at some angle, so Z will be D e raised to the power I alpha. Plus, what does it imply? A sink of the same strength at its inverse point. Its inverse point is Q dash. So Q dash कैसे जज होगा? OQ into OQ dash is again A square. This implies OQ dash is equal to A square upon B e raised to the power I alpha. This is wrong. This is not the length. AQ dash will be A square upon OQ and OQ is B. So location becomes Z is equal to A square upon B e raised to the power I alpha, because this line is making an angle alpha. So this is its location. Plus, by the image system, a source of strength M at O means 0, 0. Now you look at 1 and 2. Here you have a sink of strength M at 0, 0. Here you have a source of strength M at 0, 0. So both will be cancelled out. There will be no contribution, no final contribution. And we are left with this source, this sink and this sink. So we may write the complex potential. Now what will be the complex potential function? W is equal to M log Z minus C for this source, then this will be minus M log z minus a square upon c for this one, m log z minus b e raised to the power I alpha for this one, and plus m log z minus a square upon b e raised to the power I alpha. Now from here you may easily solve it for phi and psi. You may write z is equal to r cos theta plus r cos z is equal to e raised to the r e raised to the power I theta. Similarly here you may open e raised to the power I alpha raised to the power I alpha. You may separate it into real and imaginary part, and equating the real part you will get your complex potential. When there is a source and an equal sink within a circle cavity, and show that. So in the first part you have to find the velocity potential. That means by equating a real part you will get phi. So this is the first part. Now in second part they are saying that show that one of the streamlines is an arc of the circle which passes through source and sink. You see this circle which is passing through source and sink. And one thing they are saying that this is a streamline. You see, this is a source. So from here the fluid will emerge. And this is a sink. Here the fluid will go into this point. So this behaves like a streamline. One of the streamlines is an arc of the circle. This is the circle. This is the circle. So this is the arc of the circle which passes through source and sink. Yes, it is passing through source and sink, and cuts orthogonally the boundary of the cavity. This is the boundary. This is the boundary of the cavity. Suppose it is cutting it at N and M. So if I join this, the question says that this streamline, which is a part of a circle, will cut this cavity into 90-degree angle. And since these are the cone cyclic angles, cone cyclic points on this circle, naturally the line passing through ON will be the tangent at this point, at N, and therefore both the circles will cut orthogonally to each other. So this is the second part. It is a little bit theoretical part. You once again can very well use the theory of concyclic points and then the intersection of circles and can get this result. So this is one application. This is the application of image system. Now I am going to tell you one example in which we will use the circle theorem, where we can also use the image system and we can also use the circle theorem. So look at the working procedure. Our question is a source and sink of equal strength, a source and sink of equal strength are placed at the points plus minus a by 2 0 within a fixed circular boundary. X square plus y square is equal to a square. Show that the streamlines are given by r square minus a square upon 4 r square minus 4a square minus 4a square y square is equal to ay r square minus a square. Though I'll not solve the example up to this level, I would just tell you how we use the circle theorem. Look at this example. It says a source and sink of equal are placed at the points plus minus a by 2 0 within a fixed circular boundary. So if I draw a circular boundary and I want to place these sources and sinks, naturally this point is a by 2 0 and this point is a by 2 0. Here I have a source and here I have a sink. And you have to find the streamlines. So the one way is you use the image system. That means you find what is the image of this source with regard to this circle, what is the image of this sink with regard to this circle, and then you write the complex potential according to the arrangement of sources and sinks. Now the second way is that you have no need to draw any circle, you have no need to find the inverse points or the images. Rather, because it is a circular boundary, so circle theorem says that first you find without the circular boundary and then you modify it by adding its complex conjugate. So first of all, according to this source and sink, our system says arrangement of source and sink is source at a by 2. So source at z is equal to a by 2. It is of strength m. And sink at z is equal to minus a by 2. Same strength. So we are assuming that there is no boundary. Okay. These are just the locations. So we take complex potential W is equal to minus m log z minus a by 2 plus m log z plus a by 2. Now we use the circle theorem. I write it as fz. So using circle theorem, or to use circle theorem, what we find? We find what is complex potential of fz, or what is f z a square upon z. It is m log, in place of z I'll write a square upon z minus a by 2 plus m log a square upon z plus a by 2. So when the circular boundary is inserted on introducing circular boundary, what will be your W? You write it as W1 and you write it as W2. So what is W? W is equal to W1 plus W2, because circle theorem says that in your original Fz, in your original complex potential, you just add its conjugate. So it is m log z minus a by 2 plus m log z plus a by 2. Here it will be minus m log a square upon z minus a by 2 plus m a square upon z plus a by 2. You just solve it and you can find the equations of streamline. So this is the use of circle theorem. You may also use the image system. You may also use the circle theorem. So it is the beauty of the circle theorem that you have not to write the images, and then you have not to write the complex potential according to the image system. Rather, you just write the complex potential before the circle, just take its complex conjugate, add the two, and get the complex potential in case a circular boundary is, and then solve and get your streamlines and potential lines. So thank you so much for this lecture.